So the logarithmic function is defined as follow. Okay, the logarithmic function. So today we denote it like that. Okay. So here it is. Its definition. So let's see. So we define a new function that we denote ln as below. We defined it ln of x is the integral from 1 to x dt over t for x positive. Okay, so we can say it is well defined as because the function ft we equal 1 over t. So maybe I need to just write things differently here. So what if I do 1 over t dt? So then I have my function 1 over t is continuous function. So the area from 1 to x is well defined. And it defines a function when x is changed each time. Okay. So mainly this quantity, this number, we can visualize it like that. So suppose that I can, yes, graph my function 1 over t since I'm considering x positive. So I'm considering only the part of the hyperbola. Let's say passing 1 on this part, okay? So this is my function fx, ft, let's say, is 1 over t. Okay, now when I take, here is 1, starting from 1 to x, here is x like that here, then this quantity is ln. So this is my area ln x. Here, for this situation we are graphing here, x is positive, is greater than 1. Okay, if you want x less than 1, still it will be an area. So x or t, let's ty. Okay, and graph, consider always the same graph. So there is 1. And now if I choose my x here, somewhere here, then I will have this quantity. So this quantity, let's graph, okay, let's color it here. And so this value, the value of this quantity this time is what we call the integral from x to 1, okay, from x to 1 under the function 1 over t dt. So it is the opposite of ln. Okay, that is, this quantity is positive, then ln will be minus. So here ln x is minus x to 1 dt t dt, which is then negative for x less than 1. Okay, so my function now, I know it takes positive values for x greater than 1 and negative values for x less than 1. Great. Now, what about the derivative? Now, we have a new function. We know our purpose to study it and graph it at the end. Okay, so first thing, the domain. So let's start. Yes. First thing, domain. So domain, from the definition, by definition, we want it defined from 0 to plus infinity. So the domain of ln function is 0 excluded and plus infinity. Second, now the derivative. Okay, derivative. So I want to derive the new function. What so it's as it is defined, it's an integral from 1 to x. So we can use the fundamental theorem. So the derivative ddx of ln x is equal clearly 1 to x by the fundamental theorem. Okay, for any x positive. and then x for any x positive. That is, then I can use the monotony. So monotony, I see that my function ln is an increasing function. So it is 1 to 1. Okay. Later we will be interested on the fact that it is 1 to 1 also. Okay, ln is 1 to 1. 1 to 1. But we first now we focus on the function ln itself. Okay, so I have monotony. I can start building my table, graphing my table here. Okay, x, the domain 0, excluding 0, 2 plus infinity. The derivative ln prime x, we said it's 1 over x, so it's positive. And then we deduce then ln x, the function, is an increasing function. Great. Now, what else? We will need the convexity, concavity, convexity. Okay, concavity. So this one is obtained by taking the second derivative of ln. That is the derivative of the first derivative, which is 1 over x, which is minus 1 over x2, which is negative. So it will be concave down or concave only. Okay, so ln is concave everywhere, so concave. Great. Now we need something else. We need the endpoint behavior at 0 to the right and at infinity. We need the behavior, and then we can graph our function. To do that, so we need to know two limits. So the limit, we will use that the limit, so yes, we prove it. In fact, we prove it, that limit at 0 will be minus infinity, and limit at plus infinity is plus infinity. Okay, so those are two limits characteristic to ln function. You can keep them in mind always. And now I can graph completely my function. Okay. Yes, I can graph my function completely. So let's do it here. I have all the necessary information. Oh, yes, we can do it just here. Okay. And why? Okay. So what is ln? Yes, we said so at infinity. So we will have, when we are close to 0 from the right, we have minus infinity behavior. When x is large, when x is taking positive large values, then we have something, the y's are taking large values, the images. So we have something like that. Okay, now I need to know if there is an intersection. I know that it is a 1-to-1, which is important. Okay, these 1-to-1. So if I can find the intersection 1 point, it's enough. Now let's look at the definition of ln. ln is defined like that. So if I take in particular x equal 1, I will get 0. Okay, so at 1 we have ln taking the value 0, and like that I have the only point here that crosses the line, and I know that my shape is concave. So globally, okay, I know in advance now, globally I have a behavior like this one. So let's just erase these parts. Okay, so here is how the ln, oh sorry, so since okay, so let's do it here. Okay, so here is my ln function, y equal the shape, the global shape of our function. Okay, so now on, you know how it looks like. Okay, now just an idea how we proved some limits. We use it to prove them using properties that we can establish for the ln function. So let's write them here. some properties. Yes, so some properties here. So of course we establish them. We call them logarithm laws. If we have x positive, y positive, okay, then we can establish that ln of the product of those two numbers is ln of, maybe instead x and y, I prefer to use more a and b, so that we are not confused between the image, etc. Okay, so let's do that. A positive, b positive. Then the ln of the product eb is ln a plus ln b. Ln of a over b is ln a minus ln b. Okay, ln of x power r is r times ln x, where r is fraction, but even it's, we will later we can say that it is valid for real number, but for a moment let's say for q, rational fractions. Okay, so we have this logarithm laws, we call them. Okay, and just a hint for the limits, how we did for the limits, we took ln in particular 2 power n will be n times ln 2. Okay, then so so for x we can always, so it's clear that this limit goes to infinity as n goes to infinity. Now for okay, that is, if there exists an n0, so that for all n greater than n0, this quantity ln 2 power n, which is n ln 2, remain greater than a number m always. Okay, we can find this, but then that is for x, for m, so for m given, we can find always these n0 and x greater than 2 power n0. Okay, n0, which, okay, this is just tricky things. We are trying to check the definition of limits, that's all. So ln x greater than ln of 2 power n0, which is n0 ln 2, which is greater than m. So this says that the limit of ln, so limit, we can say that limit of ln x is plus infinity as x plus approaches plus infinity. So this is the idea. So it uses clearly these properties. Okay, and these properties also we deduce them coming back using the fact that the function is inverse. So coming back to what is ln f minus x equal y equivalent to x equal etc. Okay, so there is nothing difficult about that. For the limit to close to 0, we write just ln x as minus ln. We use the rows. So as x, so this approaches, as x approaches 0 plus 1 over x approaches plus infinity, so it's approaches minus as x approaches 0 plus. Okay, so this is the idea about this. What else you should know? There is something else. Since we have a one-to-one function, it is here the value of, we have ln, so let's put this as a remark, important remark. Okay, remarks. So we have ln1, which is 0. Okay, we found it 0. Then for x, now we know that we can, by the intermediate value theorem, the value 1, y equal 1, is reached, is attained somewhere. And this value, this is what we call e. Okay, we know, but by the intermediate value theorem, there exists a c, which is e, greater than 0, such that okay, such that ln of this e is 1. And this value e is the Neperian number. It's an irrational number, so e belongs, we show that it is irrational, it cannot be fraction. And its value, we prove that it is all close to 2718. Okay, so it's number, important number. Also, you can add here other reference to plot your function. Okay, that's all. Otherwise, the rest now, knowing a new function, then we can do many things. We can be interested combine them with the new other functions we know and form new other functions, and we can be interested in studying them, graphing them, etc., etc. Okay, one more thing, one last thing to know, good to know, is about logarithmic differentiation. Logarithmic differentiation. So it's good to know it because it's very useful. It simplifies a lot of calculations. So let's see it through an example. What about this function, given function x2 plus 1? I see it's fraction, okay, and with power, combined with power functions, with radicals, etc., etc. So I have fraction and product, so I can use the usual rules of differentiation for ratio and product and do my calculation. But it will be too long compared if I decide to take the ln of this expression. So I use the law of ln's. So I have a ratio, so it will be the ln of the numerator, x3 power 4 square root x2 plus 1 minus ln of 3x plus 2. You will see how it is practical. Then, second step. Here I have a product of two numbers. Ln of the product of two numbers is ln of a plus ln b. So it will be ln of x3 over 4 plus ln of square root of x2 plus 1 minus, here I have ln of number power, so I will use the third law. It's the power ln, so it's minus 5 ln of 3x plus 2. Great. Here also it's still we have a power, so it will be the first term we have power. Square root also is a power, or 1 over 2, so I can write it 3 over 4 ln x plus 1 over 2 ln of x2 plus 1, okay, minus 5 ln of 3x plus 2. Now look at what I'm going to do. I will take the derivative of the ln y. Okay, so it's a combined function. So I will derive the other side. So it will be 3 over 4, the derivative of ln, which is 1 over x, plus half the derivative of ln of x2 plus 1. But this is, I need the chain rule formula for this one. I need the chain rule. The chain rule says I will derive the first function, gives me 1 over what of the second function, x2 plus 1, times the derivative of the second function, which is 2x. And the same for the last term. So it will be 1 over 3x plus 2 times 3. Here it is. Once I have this right side, let's go back to the left side. Left side, I see I need to look at this term as composite function also. So it will be the derivative of ln. So this one, let's use another color for this one. So for this one, it's the derivative of ln. So it's 1 over applied to the second function y at x times the derivative of y, which is y prime at x. Okay, finally y prime, so y, the question was about the derivative. Okay, it will be y of x, which is, so y of x, y, so you see y times the whole term, the whole this term here. Okay, and y, we know it's the given by the expression, you see. So you see how it is practical and simplifies a lot of our calculation. Okay, so this is about L. Now you have to practice a lot with the new function. You have all the theorems. You can have questions around this theorems we saw, chain rule, studying new functions, etc., etc., computing areas, etc., etc. So just practice.